Hello everyone. In the last session, we have learned about image enhancement in the spatial domain. So that is module 3. Now, heading towards the module 4. In module 4, we will be learning image enhancement in the frequency domain. So, in the last chapter, we have already seen the spatial domain. Now, in this chapter, that is in this session, we will be dealing with the frequency domain. Okay, so the contents of the image enhancement in frequency domain module are the background of the image enhancement in frequency domain, introduction to the Fourier transform and frequency domain, smoothing frequency domain in the domain filters, then sharpening frequency domain, that is again the domain filter, then harmonic filtering implementation. Okay, so in the last session in the module 3 we have also learned the smoothing frequency and as well as sharpening frequency. Okay, but smoothing spatial domain, that is SSD, smoothing spatial domain and then sharpening spatial domain. Here smoothing frequency domain, then sharpening frequency domain. Okay, so let us see the background. So Jean-Baptiste Joseph Fourier is a scientist who have invented this Fourier transformation. Is a greatest researcher. His surname Fourier has been kept for the Fourier transformation. So Fourier transformations and Fourier series. There are two types. Fourier, that is Fourier series and as well as Fourier transformation. My question is, what's the difference between Fourier transformation and Fourier series? Are they same? Where a transformation is just used when it's applied? Yeah. So the answer is no, that they are not same. They are different. Okay. So we'll be seeing at what is Fourier series now. Fourier series simply states that periodic signals can be represented into sum of sines and cosines like this, and when multiplied with a certain weight. Okay, it further states that periodic signals can be broken down into further signals with the following properties. The signals are sines and cosines. The signals are harmonics of each other. It can be pictorially viewed as like this, sine and cosine. Okay, so how it is calculated? Since frequency domain, in the frequency domain we are dealing in this module. Okay, the image should be first converted into the frequency domain and then we have to apply the spatial domain for that one. So that is how both Fourier series and Fourier transformation has got two formulas, one for conversion and one converting it back to the spatial domain, because spatial domain we're going to see the noise free images. Okay, so in this section, we'll be seeing one dimension and two dimension Fourier transformations. Okay, so one dimensional Fourier transformation and its inverse looks like this. F of u is equal to integration of infinity to minus infinity f of x e to the power of minus j into 2 pi mu x. Okay, so infinity to minus infinity, there we were seeing in the spatial domain as 0 to 1. Here we are seeing minus infinity to the infinity, because there we were directly dealing with the matrix either 0 or 1, but here we are dealing with the frequency, that is why minus infinity to the infinity. Okay, so the periodic changes, whatever it is happening there, with those periodic changes we are dealing in the frequency domain. That is why it is averaging in between infinity to minus infinity. So f of x, you already know, this is a single dimensional image we are talking about. That is why x is a single pixel. E to the power of minus j 2 pi ux is nothing but some constant, where ux, here ux is for the single dimension and ux plus uy for the multiple dimensional Fourier transformation. The inverse of this equation can be written as f of x is equal to integration of infinity to minus infinity f of u e j to the power of e to the power of j 2 pi mu x into du. Okay, here minus will be coming and here plus will be there. Okay, so two-dimensional, let us see. In the previous slide, we have seen f of u and f of x. Here, two-dimensional, we are seeing f of u comma v and f of x comma y. So f of u comma y can be written as integration of infinity to minus infinity 2 times double integration f of x comma y into e to the power of minus 2 pi ux plus vy. So we have seen here only ux is there, here ux plus vy, because it is a two-dimensional Fourier transform. So inverse of that one can be written as f of x comma y. Okay, double integration from infinity to minus infinity, that is capital F of u comma v into e to the power of j 2 pi of ux plus vy, the coordinate values du du. Okay, so we have learned about the Fourier series. Now we shall see what is the Fourier transform. So it simply states that it is all about the non-periodic signals. Okay, Fourier series was dealing with the periodic signals. Fourier transform deals with the non-periodic signals. Okay, whose area under the curve is finite, can also be represented into integrals. The Fourier transform has many wide applications that include image compression, filtering, and as well as image analysis. Okay, so difference between Fourier series and transformation. Although both Fourier series and Fourier transform are given by Fourier, the main difference is Fourier series is applied on the periodic signal, as I've already told. Fourier transformation is applied on non-periodic signals. So which one will be applied on the image now? Either the Fourier series or the Fourier transformation. Okay, so let us see in the next slide which one is applied on images. Now the question is that which one is applied on the images, the Fourier series or the Fourier transform? Well, the answer to this question is about the image. Image is always the non-periodic. Okay, and since images are non-periodic, Fourier transformation is used to convert them into frequency domain. So images are discrete, that is why discrete Fourier transformation we'll be learning now, since we are dealing with the image and in fact digital images. So for digital images we'll be working on discrete Fourier transform. It will be having three things considering the image like this: spatial frequency, magnitude, and a phase. Okay, there are three things: spatial frequency, magnitude, and phase. So what are these? How are related to the images? Discrete Fourier transformation will be having three things, that is spatial frequency, directly relates with the brightness of the image, then magnitude, which is directly relates with the contrast, then phase, which contains the color information. So frequency will be dealing with the brightness of the image, spatial frequency, then magnitude, which relates with the contrast, that is low contrast or high contrast, then phase, which contains the color information of the image. Okay, so discrete Fourier transformation equation can be given by in one-dimensional format. F of u is equal to 1 by m, summation of x is equal to 0 to minus 1, then f of x e minus j 2 pi 2 pi mu x. Okay, then inverse discrete Fourier transformation can be written as f of small f of x is equal to summation of x is equal to 0 to m minus 1, and then capital F of u into e to the power of j 2 pi u x. So ux is for the single transformation, then ux plus vy is for the two dimensions. Okay, so introduction to the Fourier transformation and frequency domain. In the frequency domain, so frequency domain, some of the applications analysis shows the signal's energy which is distributed over the range of frequencies. Also it gives us the control over the whole images. then it is very easy to enhance like edges, and then lessen the smooth shadows. Okay, then frequency domain methods are based on the Fourier transformations. We already know that. Then below image, this image shows that how this spatial domain image is being transformed to the Fourier transformation using the frequency domain. Okay, so let us have some glance over the spatial domain, which we have learned in the previous session. In the spatial domain, we deal with the images as it is. There is no need to extract the values of the pixels which change with respect to the scene. Okay, whereas in frequency domain, we deal with the rate at which the pixels values are changing in spatial domain. I explained in the previous slide that spatial domain is directly dealing with the images, like I have shown in the image input matrix is there. We're going to process with this matrix, and we're going to get the output matrix. But frequency domain, we're going to deal with the process of that one. Okay, like this. Okay, frequency domain input image will be given, the frequency distribution is done, then on this frequency distribution processing will be done, then after processing inverse transformation is done to get the output image. Okay, so image transformation mainly allows follows three steps. Step one, transform the image. Step two, carry the task in the transform domain, then apply inverse transform to return to the spatial domain. This one is represented like this. Okay, f of x comma y is the original image, t of u comma v is the transformation you're going to apply, then r is the reverse transformation, okay, to get back the transformed image, that is g of x comma y is the transformed image. Okay, so in the previous sessions, whatever we have seen was just like this: g of x comma y is equal to t of f of x comma y. Okay, so transformation was directly applied on the original image matrix, and you used to get the frequency, that is what do you call it, special domain image, that is transformed image. But here f of x comma y is first transformed, okay, using some transformation, then inverse transformation is applied on this f of x comma y, then only we're going to get g of x comma y. Okay, so the difference between the spatial domain and the frequency domain is this. Okay, so in the frequency domain only one level transformation was happening. In the frequency domain, two levels, that is first transformation on f of x comma y, and then inverse transformation on f of x comma y. Okay, this you can see it here. Okay, now we shall see some equations in the Fourier transformation. So to express f of x in polar conditions, we have got certain things, that is f of u. We already know that f of u is equal to magnitude of f of u is equal to e to the power of minus j by u for the single domain. Okay, then capital F of u can be written as r of u square plus I of u to the power of minus 2 to the whole square. Then magnitude of f of u is called as the magnitude or the spectrum. Okay, then here phi, in this image, this phi is called as the phase angle or the phase spectrum. Then P of U is called as the power spectrum of power density, spectrum density. This we have implemented in the class, and we have seen the demonstration live in live. Okay, so there are three types. One is magnitude or spectrum. In the internals, we may ask that magnitude or spectrum. Okay, please explain with the equations about the polar conditions of f of x. What are the polar coordinates? Magnitude or spectrum, phase angle or phase spectrum, power spectrum of spectrum density. Okay, let us see how actually it works. Okay, these equations are directly given here. Combining all these things have been given here directly. Okay, what is the first one? Is a spectrum or magnitude. The second one is phase angle or phase spectrum. The third one is power spectrum of spectrum density. Okay, the examples of this is the image of 20 cross 40 white rectangle is used on a black background of size 512 cross 512 pixels. Okay. Second image shows the centered Fourier spectrum shown after the application of the log transformation. Okay, log transformation we have already seen how actually it looks like log transformation in the frequency domain. Okay, there are a few more informations. This is these are the original images. After applying these templates, you're going to get this kind of outputs in the frequency domain. Okay, so when you apply the magnitude of the spectrum, the first image was showing, second one was the phase angle, and the third one was power spectrum. Okay, so when you apply the magnitude of the spectrum and the phase angle and as well as the power phase, you're going to get these outputs. Okay, now steps of filtering in the frequency domain, we have got 6 steps. So let us see the step by step. Multiply the input image by -1 of x plus y. Okay, so there in the spatial domain we were seeing that we were multiplying the mask by 1/9 or 1/16. Okay, to get the averaging mask or averaging filter or low pass filter. But here what we are doing is we are multiplying with the -1 of x plus y to center the transform. Okay, you may ask why. To send answer is to center the transform, and the equation is given by f of x comma y into -1 of x plus y. The final equation you're going to get has f capital F of u minus 1 by 2 and then v minus n by 2. Okay, so f of comma y into -1 of x plus y. When you multiply this one, you're going to get comma v minus n by 2. Whereas in spatial domain, you are directly getting ux comma vx. Isn't it? This is spatial domain and this is frequency domain. Okay, so compute f of u comma v, the discrete Fourier transform of the image, then multiply f of u comma v by a filter function h of u comma v. Okay, so g of u comma v is the transformed image. H of u comma v into f of u comma v will going to multiply with the h of u comma v. Okay, this h of u comma v is the filter function, f of u comma v is the original, and this is the transform. Okay, compute the inverse discrete Fourier transformation for this result. Okay, filter image you're going to get capital G of u comma v. Okay, so I have already told you people that in the spatial domain you will be working on G of x comma y. This is the transformed image is equal to T, capital T is an operator of f of x comma y. Okay, so this is the original image, T is the operator, and G of x comma y is the transform image. In the spatial domain we were working like this, but in frequency domain, G of x comma y, if you want to get G of x comma y, you need to in the first step you need to apply transformation of f of x comma y. So you need to apply that one. So here frequency distribution is done. Okay, inverse of f of x comma y. Okay, so now compare this one here, compare this one with this steps. So here what you are doing is you are multiplying with -1 of x plus y to get the distribution. The distribution is given as f of u minus m by 2, then v minus n by 2. Okay, so you need to compute the discrete Fourier transformation for this first step, that is f of u comma v. So if you want to get the discrete Fourier transformation at the first level, you need to multiply with some function. Okay, here we are calling it as filter function h of u comma v. So f of u comma v and f of x comma y are one and the same. Here x and y terms have been written as u comma v here. Okay, let me take u comma v itself only. So here what we are doing here is f of u comma v, this t is nothing but h of u comma v. This t. Okay, t is nothing but h of u comma v. Okay, then inverse transformation. Okay, this is transformation is happening, this is inverse transformation is happening here. Okay, then inverse transformation, that is t inverse of f of u comma v. You're going to get the final result. Okay, so I repeat once again. In the Fourier transformation in the frequency domain, what we have to do is first to take the original image, that is f of u comma v, then apply some transformation, that is t of f of u comma v. Here t is nothing but some function. Here we are calling it as filter function. So t here is h of u comma v. Okay, so h of u comma v into f of u comma v, you're going to get one transformed image, that is g of u comma v. In order to get the original image, you need to do the reverse transformation because frequency has been distributed here. That is why you're going to get the original image when you multiply with the inverse. Okay, till here you have understood about the introduction of Fourier transformation and the frequency domain. In this one, we have learned steps of filtering in the frequency domain. Okay, next, whatever I have told, it is a pictorial representation. So here pre-processing f of x comma y is the input image. Pre-processing is done here. Then Fourier transformation, you're going to do f of u comma v. Filter function, you're going to use h of u comma v. You're going to multiply this h of u comma v with the original image, that is f of u comma v. Okay, here you're going to do. Then inverse transformation, you're going to do multiply by minus 1 of minus 1 to the power of x comma y. Then you're going to get post processing, that is g of x comma y enhanced image. So the process consists of 4 stages: input image, pre-processing first stage, second, third stage, and fourth stage. Pre-processing, Fourier transformation, then filter function, inverse Fourier transformation, post-processing, we're going to get g of x comma y, this transformed image. Basic steps of filtering in frequency domain. Okay, so the filter, this h of u comma v filter, how does it look like in the pictorial representation? This is how it look like. Perspective plot of this first image is the perspective plot of an ideal low pass filter, that is transfer function. The second image is the filter displayed as an image. This one is displayed. This box is there, no, that is black color one. This top one is this. Okay, u comma v, this one. And if you want to see graphical representation, this is the third. Okay, so this is the perspective plot of an ideal low pass filter in the 3D format, in the 2D format, in the graphical format. Okay, so smoothing frequency domain has got the equation g of u comma v is equal to h of u comma v. Okay, one second. Okay, so let me write it compared to the spatial domain. Okay, this is frequency domain. In the spatial domain, we used to write it as g of x comma y is equal to t of f of x comma y. Okay, so g of x comma y is here, t here is g of u comma v. So h of u comma v is what here? That is a filter function. Okay, f of u comma v is a original. Here this is x comma y is original, here f of u comma v is original. This is transformed image, this is also transformed image. T operator, it was working on the single pixel, and this is working on the multiple pixels. So ideal low pass filter, this h of u comma v, here we are considering as the low pass filter, will be working in between 2 pixels, that is 0 and 1, black and white. Okay, 0 and 1. If d of u comma v is less than or equal to d naught, then 0 if d of u comma v is greater than d naught. So d of u comma v u minus m by 2 whole square plus v minus n by 2 whole square. This we have seen in the previous steps, previous slides. I'm seeing that we have studied that one. Something we have seen in the previous slide. Yes, here. This one, f of u minus 1, u minus m by 2, v minus n by 2. Okay, this is what we are seeing here. This is one. Okay, d naught is called as the cutoff frequency. You might have got the doubt that what is this d naught. Okay, I'll explain once again. So we already know what is g of u comma v. What is that? Yes, exactly. G of u comma v is the transformed image. H of u comma v is a transformation operator. Here it is called as low pass filter. Okay, f of u comma v, it's a original image. Okay, so h of u comma v will be working under two conditions. If it is 1, the cutoff frequency should be less than or equal to, that is cutoff d naught. D naught is the cutoff frequency less than or equal to 1, and then 0 if the cutoff frequency is greater than d naught. Okay, so d of u comma v, d of u comma v can be called as u is equal to m by 2 whole square, and v with respect to v minus n by 2 whole square. M and n can be called as the x and y coordinates here. Okay, so choosing the cutoff frequency according to the power spectrum of an image, we can write it with the summations of u and v, as we are dealing with this one. There we were calling it as a PR. Here we are in the spatial domain we are calling it as a PR. Here we are calling it as P of u comma v. Summation of u is equal to 0 to m minus 1, and summation of v is equal to 0 to n minus 1, and P of u comma v, summation of everything. Okay, where alpha is equal to 100 of summation of u v to 1 and P of u comma v by pt. Okay, the power spectrum we were talking about, this is the power spectrum of an image, where an image, this first image is a size of 500 cross 500 pixels, and second is the Fourier spectrum. The circles, you're seeing two circles, is totally based on different radii. Okay, the power spectrum of this image is this Fourier, using Fourier transformation. Okay, so blurring and ringing effects, frequency domain, we already know. Already we have seen these two. I have already explained in the previous slide. Okay, in the frequency domain, this is the, again I have to repeat this. G of u comma v is the transformed image. Here this is the transformation. F of u comma v is the original image. In the spatial domain, in module 3 we have seen this is the transformed image. Here h of x comma y is the transformation t, and f of x comma y is the original image. Okay, blurring with respect to the low frequencies are removed, and the ringing cutoff is too sharp. Okay, fine. Okay, so these are the examples, some of the examples. So we are seeing two sides here. This is the small dot and a small dot more than this one, and the frequency domain, how actually it works. Okay, with a frequency domain, ILP of full form is ideal low pass filter of radius 5, then corresponding spatial with 5 pixels been done here. Okay, then convolution of these two is been given here, how actually it works. This we have seen in the MATLAB when we were studying in the class, that is how the spectral works. Okay, smoothing frequency domain filters, A to D, A, B, C, D. This one I think you might get confused, that I have put it this way. Okay, 1, 2, 3, 4, the same thing here. Okay, so spatial spectrum of the low pass filters of order 1, 2, 5, and 20. This is order 1, this is order 2, order 3, order 4. Like these are all the spectrums. Okay, and these are all the graphical representations of those spectrums. Okay, one more example. Here you can see how actually it is broke down. Okay, here you can see result of the low pass filters, how it will going to help to get the connectivity. Okay, of course this is too smoothened. In order to overcome from this smoothened image, what we have to do, we have to use sharpening. Okay, so in module 3 we have learned smoothing spatial domain and sharpening spatial domain. Smoothing spatial domain is improving the pixels in the image by smoothing that one like this, and sharpening is coming back. The small difference here is we are working with the frequency domain. We have already seen what is the frequency domain, and this till here it is smoothing is being done. The reverse process is sharpening frequency domain filters. This is using smoothing frequency domain filters. This is one example. Okay, one more example of the eye, the wrinkles. I think many of you people have done the Photoshop to put your DPs in social medias like Facebook and WhatsApp. Okay, will you go and directly put like this? No, So you're going to enhance your image. This is the enhancement procedure. Okay, so where and all you can use the DIP. Okay, the there we have seen the h of u comma y. This is h of u comma v. So this h of u comma v is nothing but the filter. Okay, filter function. Okay, the first one, second one, third one, and fourth one, third one, all three of different types of sharpening frequency domain filters you're seeing there. Okay, so the exactly opposite. See, if you see here, what is you people are seeing here, the smoothing frequency domain filters graphical representation is coming upside. Okay, upside the x-axis. Then in the sharpening frequency domain, it is falling below. Okay, so the main difference here is in the smoothing frequency domain. In the smoothing frequency domain, the image is smoothed. Okay, okay, this is the original image, and you're going to apply t, that's some transformation functions, that is h of u comma v directly. Then you're going to get the smoothed image. Okay, the input for the frequency sharpening frequency domain is, that is FFD, which is the smoothed image, and you're going to apply reverse in transformation, inverse transformation. Then you're going to get the sharpened image. Okay, so here you can see the spatial representations of the typical and ideal Butterworth and as well as Gaussian frequency domains here. Okay, then the last one, that is a homomorphic filtering. This is the last point in the fourth module syllabus. Okay, homomorphic filtering is nothing but the combination of gray level, range, compression, and contrast enhancement simultaneously we're going to do in the homomorphic filtering. Okay, so the first point here we are explaining it, simultaneous gray level compression and contrast enhancement. So here also you remember, whatever you people do, whether it is the spatial domain or the frequency domain or harmonic harmonic filtering. Okay, just keep it in mind, that is f of x comma y is equal to t of f of x comma y. Okay, this equation you remember, f of x comma y is equal to t of f of x comma y. Okay, so this is a special domain equation. For the Fourier transformation, f of that is x comma y into f of x comma y, you are multiplying the original image with the filter. Okay, here also f of x comma y is being distributed as I of x comma y and r of x comma y. Okay, so gray level transformation and as well as contrast enhancement, you're going to get the homomorphic image. Okay, inverse of this one, transformation, you can write it as a transformation. F of x comma y may not be equal to transformation of I of x comma y and transformation of r of x comma y. Okay, so this is some explanation about this. You can go through that one. Continuation of that one, s of u comma v is the transformed image. H of u comma v, what is h of u comma v? Is a filter. Z of u comma v is the original image. So combination of both of these two, that is combination of what, gray level image and contrast enhancement image. This is for the single dimension, this is for the multiple dimensions. Okay, so inverse of this, you can call this one as like this, s of u comma v is equal to s of x comma y. Okay, this is transformed, this is original. Okay, so complete equation h of u comma v and f of u comma v plus h of u comma v, fr of u comma v can be called as, in the previous slide you have seen, no, that is uh, R and I, what are the two different things? One is gray level and another one is contrast stretching. Okay, can be called it as x comma y. Okay, so here I of x comma y and r of x comma y, the same is being used here. F of h of u comma v and z of u comma v can be derived as h of u comma v fi, that is this I of x comma y, fi of u comma v plus h of u comma v, that is h of u comma v is nothing but the filter, then r is nothing but the contrast enhancement, fr of u comma v, and the inverse transformation of this. So in general you can write that s of x comma y is equal to I of x comma y, r of x comma y. Okay, So homomorphic filtering equation is like this: f of x comma, this is as similar as this graphic, pictorial representation of the Fourier transformation, this one. Okay, so this is for the Fourier transformation, this is for the homomorphic filtering. Okay, so this is the input image. So discrete Fourier transformation you're going to apply. H of u comma v is what? Is a filter. Then df t of inverse, that is inverse transformation. Then post pre-processing you're going to do, you're going to get the g of x comma y. Okay, this is homomorphic filtering example. Okay, so now in the last session we have studied the frequency domain. Okay, that is image enhancement using the spatial domain and as well as frequency domain. Two types we have seen. Okay, image enhancement and frequency domain. Spatial domain also we have learned, frequency domain also in this module we have seen. Okay, so we have seen the background, the Fourier the researcher by name of Fourier has introduced this Fourier transformation. Then introduction to the Fourier transformation. There are two types: Fourier series and as well as Fourier transform. Fourier series is applied on the periodic functions, whereas Fourier transformation on the non-periodic functions, that is discrete one. Okay, that is why Fourier transformations is used with the images. Here, that is smoothing frequency domain filters and sharpening frequency domain filters. Then we have studied about the homomorphic filtering as well. Given you people the notes, then PowerPoint presentation, and as well as the question bank. Okay, on April 14th, I want both the module 3 and module 4 assignments so that I can evaluate the marks for you people on the assignments for you people will be full. Okay, so till then, be safe, don't go outside. Okay, let us meet on 15th April. Okay, if time permits, if everything goes fine. Okay, so now bye, we shall meet again.